So we've had a few talks about frame matroids and kind of close to graphic matroids. I will be talking about another class of these, closely related things, but these are going to be represented over a field. A bit of the motivation comes from this infinite family of excluded minors for frame matroids that Rung Chan and Jim Gillen found. It has the property that all these matroids have a branch width 4. They all have low branch width. And kind of what we showed is that if you restrict yourself to this class of represented matroids, then suddenly you can't have this case anymore, because if you bound the branch width, you bound the size of the matroid. So I need to define a little bit what I mean by represented matroid. I will have a field. This field doesn't have to be finite. And then I will define a matroid as something that simplifies to a projective geometry. The simplification is just to allow for parallel pairs and things like that. And I will just pick a subset of elements from this geometry. I will say it's a frame if I can find a set of points in my geometry so that this set is independent, and every element is contained in the span of 2 elements of my vertex set. I'm calling this special set of elements the vertex set. Of course, this naturally defines a graph, as we have seen before. If I have an element between 2 of these vertices, I just add an edge between them. If I have an element exactly on one of my vertices, I just add a loop. So how do you prove something about branch width? A very natural tool is to talk about separations that are nested, since in a 3D composition for the branch width, you would have a long list of nested separations would give you a long path in this tree. So it's kind of a natural way to look at it. I'm going to say the separations are nested if basically the left-hand side contains the left-hand side of the next separation, so on and so forth. So it kind of looks like that picture where I'm adding things on from the right to the left. The order of the separations is all kind of given by some k. And I'm going to say the separations are linked if the connectivity from the beginning to the end of my sequence is maintained. So it is k in between the separations, and it's k throughout the sequence. So here's what we actually proved. If I have an excluded minor for the class of represented frame matroids, then I have at most some number of nested k separations. And the statement I said before just follows as a corollary. So in order to look at this, I need to look at separations in the matroid and in graph representations of this matroid, right? So I look at a separation in a framework or in a graph representation for this matroid. I have different cases. Either it is a normal graph, all the cycles on one side correspond to the cycles on a matroid, and then it's balanced on that side, or it doesn't and it's unbalanced. And I need to consider all these 4 cases. So when I have a representation where both sides are unbalanced, one side is balanced and one side is unbalanced on both directions, and when both are just balanced on their own, but perhaps don't meet up in the right way. Now, a nice thing is if I have one of these sides as unbalanced, then I can, in a way, certify whether this is a frame matroid or not. There is a way to tell whether these 2 things don't match up together in that way, in those representations by a certificate that there's only finitely many. So it's kind of nice. In the last case, I cannot, but I just have to treat it differently. So here's a proof sketch. I start with an excluded minor with a lot of nested separations. And I know from this lemma by Ben David and Jim Gillen that if I have a lot of nested separations, then I have a lot of linked nested separations. So I can find a long sequence of separations that have this nice connectivity property throughout. What this gives me is the possibility of contracting out one of these separations by using Tutte's linking theorem and preserve the connectivity in the sequence. So, okay, so I have this long sequence of separations, and I can look at how they interact with each other. So if I contract one out, I get a graph because this is now a represented frame matroid. So I have a graph, and this graph has one of these forms. Now, I cannot have too many separations of this type, unbalanced, unbalanced, because before I contracted, those separations were already there. And if I have enough of these, 2 of them were failing for the same reason, right? I contracted this out, and I got a frame matroid that doesn't look the way it's supposed to. So I wasn't looking at the right form of this, at the right representation for this. There's only so many. I can do the same for the balanced unbalanced case, and there's only so many separations of this type, and there's only so many that will have this type as well, the unbalanced balanced. So I end up with a fairly long separation, a long subsequence of separations that whenever I contract one, I get a graph that is balanced on both sides of my separation, and all the unbalanced cycles go around. This basically will look a lot like a flower. I have something that's basically graphic locally with all the unbalanced cycles going around and going through all the petals of this flower. Now, this is close to graphic, and we understand fairly well what the matrix the representations for graphic matroids are. So I contract one of these petals out, and I get a graph. I take the next one, and I contract one out, and I get a graph. And this graph is very, very similar to the old one, because each of these petals is really, really close to 3 connected. So I'm getting something that is basically the same graph with a small segment that is a little bit different. Now, what happens if I take 2 segments that are far away, like the 2 I have indicated on this slide, and I contract one on one side and one on the other? I get 2 graphs that are really, really similar. In fact, if I can get a graph when I contract both of them, it gives me the same graph in total. And then I can take one of them and replace each of these segments in my graphs. So I can kind of do a Frankenstein trick and glue the segment that is close to, like this segment that surrounds this area in the matroid I got from contracting it, and kind of build it back up, and I get a graph. Now, it turns out this graph is a framework. This matroid is now quasi-graphic, and I have a framework for it. And I also have this nice theorem by Jim, Bert, and Jeff Whittle, which he described earlier today, that tells me that in this case, since I now have a 3-connected representative quasi-graphic matroid, then this is either frame or lifted graphic. And I also know that I can find 2 disjoint cycles going around this structure. And Jeff pointed out earlier, this is exactly the distinguishing case between frame and lifted graphic. If those 2 disjoint odd cycles are a circuit, then I am lifted graphic. If they're not, then I am a frame. And it turns out that I can find these so that they go through one of the sets I contracted. So when I contract this set, these 2 cycles are still disjoint. And this new frame I got by contracting this I know is a frame matroid. This I know is a represented frame matroid. So those 2 are not a circuit there, and they were not a circuit in the big graph. Thus, this was not a lifted graphic matroid. It is a represented frame. That contradicts my assumption that it was an excluded minor. Some closing remarks. I can use similar ideas with lifted graphic matroids. These 2 classes are really quite similar to each other. So one can trace this proof using lifted graphic instead of frame, and it reasonably easily follows. And the other thing is, this kind of removes the case that we know goes wrong with frame matroids. So there's still a good chance that this class has only finitely many excluded minors. Thank you.
All right, any questions for Cynthia?
So you don't need to be 3 connected. I'm hiding a lot under the rug there. It just, whenever you have a two separation, you can do some tricks to get around it.
And also another question is, can you explain like a case when the matroid is framed, but the data graph, like the plot graph, representation is not framed?
So if it doesn't look like this, and it has a lot of separations, I will find a set of separations that looks like the unbalanced case. So if I don't have something that looks like this, I only have so many separations, or something went wrong, basically.
Any further questions?
What do you consider the matrix is representable? What makes it difficult for the alternative but flat matrix?
I didn't understand that, sorry.
Okay. So you just consider the excluded minor for representative matrix of some bounded parameters. I mean, what makes it difficult for consider the ordinary flat matrix is not representative?
Oh, so if you remove the representedness or the representability of the matroid, you run into issues with the techniques we're using. So we are using a lot of the representability to be able to certify why these two things don't get together by putting points in between a separation. And a lot of those things, you can't just add points easily when you don't have representability. Yes, you can for this case. The problem is with the other two cases. I do believe that infinite families for that case will also end up with this weird structure. I just don't know how to prove it.
Just because you use this theorem, or just because you use other elements? Oh, okay.
So yeah, no, this theorem does not apply if you're not representable. So this is the ingredient that we have that is actually different between these two cases.
So the other things you need added elements.
Yep.
Okay.